Our next talk will be from Kyle Finner. Kyle is here at Caltech IPAC. Kyle, I'll give you a flag at 3 and a flag at 1.
Okay. All right, thank you. So yeah, I'm Kyle. I'm a staff scientist here at IPAC, and today I'm going to talk to you about studying the formation and evolution of galaxy clusters with Roman weak lensing. So I put this cold dark matter simulation here to show that the universe forms a large-scale structure of clusters and filaments spanning between the clusters. And I'm just going to quickly skip on to a zoom-in simulation on the formation of these galaxy clusters. So there's cold gas in green, hot gas in red, and stars are in white. We get the formation of two galaxy clusters here, one on the left side of the simulation, one on the right. And this is a gigayear process that's happening as these are forming. Hot gas is being blown off. And I spoke a little fast, but they'll collide soon. So they'll collide at a supersonic velocity. And I'll try to stop it right there. So we get the formation of shock waves leading in front of the two clusters as they're merging. So there's lots of interesting features, and these are some of the most energetic events since the Big Bang, these cluster mergers. There's a lot of interesting physics to study in galaxy clusters. I think one of the more famous ones is dark matter. So in the figure in the left here, we have the bullet cluster. It's a very famous cluster merger from Claudel 2006 here. And they've mapped out the dark matter distribution using weak lensing and shown that it separates from the ICM, which is emitting X-rays. And from this, they were able to put a upper limit on the self-interaction cross-section of dark matter. Another way to study dark matter in clusters is to look at the radial density profile, as shown in the top right here from this paper by Umetsu. And they've compared the stacked radial density profile of clusters to the NFW profile in the top right. There's a lot of interesting physics going on in the intercluster medium, and we can look at the evolution of the ICM by studying many clusters. As I already mentioned, we get the formations of shocks. And we can also study magnetic fields and something called radio relics. So in the bottom left here, we have the sausage cluster. This is the X-ray emitting intercluster medium in green, and you can see it's clearly elongated along the merger axis. These clusters have collided. And shocks have formed. We have a shock in the south, shown here in jet, and one up here in the north. And this is the sausage relic in the north, this really nice arc-shaped merger-induced shock wave that's emitting synchrotron emission from electrons being accelerated in the magnetic field at the shock front. And there's a few outstanding problems in our understanding of how these form. So one is the electron acceleration mechanism. The leading model is called diffusive shock acceleration, DSA, and how efficient DSA is in accelerating electrons. In the bottom right, I show a comparison of the Mach number measured from X-ray versus the Mach number expected from DSA. And you can see there's clearly a discrepancy in those Mach numbers. So one of the leading theories for how we can resolve this is using a population of superthermal electrons that exists in the ICM near where the shock wave's propagating. And how those get there, we're not quite sure yet. So studying clusters like this is challenging because the timescales of clusters are gigayears long, and during our lifetime, we only get a single snapshot of what a single cluster looks like. So we need a lot of clusters to try to study them. And then they're filled with a large variety of astrophysics, and I think radio is a good way to show this. So here we have our radio relic, synchrotron emission, but we also have the AGN jets that look somewhat similar. They're megaparsec in size. So it's hard to disentangle the different astrophysics that are happening. So one approach we take is to get as much multi-wavelength data as we can on clusters. We get X-ray, radio, we use weak lensing and do spectroscopy. Here I've listed a lot of the measurements that we can make to try to understand the galaxy clusters and the mergers that have happened. We take this data and either create idealized simulations or look for analogs in cosmological simulations that match our observations, and then we compare them. We take what we see in the simulation to what we see in observation, and then we try to understand things like the nature of dark matter, shock acceleration, and magnetic fields, and other things. So I'd like to demonstrate the value of weak lensing to this process. This is Able 2255. It's at a redshift of 0.08, so it's really nearby for galaxy clusters, I'd say. And this is a Subaru color image. You can see the bright cluster galaxies here in the center. This is a paper from 2020 of the same cluster, Able 2255. It's LOFAR data, 150 megahertz radio observations. They called, the title of the paper was The Beautiful Mess, and it's quite a bit of a mess in radio. You have all of these AGNs, head-tail galaxies like this, the beaver they called it. You have the T-bone here in the center. And then here's the shock wave, this very diffuse emission up here that's really hard to see, especially at 150 megahertz. Here's the cluster in Chandra X-ray observations. This just ball of gas. It doesn't really seem to show much. No real insight into the merger that could have created that shock wave. And here I've put the the radio contour from the shock. Using weak lensing, we can map the mass distribution, which gives us pinpoints on where the dark matter peaks are. There's clearly an east-west elongation in this cluster, but if we look in the west, now we see two peaks that somewhat align with that shock wave, that radio relic. And so weak lensing is great for identifying these substructures that could have collided in the past to create the shocks. And here I've drawn a line showing you that past collision. So that shows the value of weak lensing to understanding the formation of clusters. So now I'd like to move on to show you how Roman will be very valuable for weak lensing of studies of clusters. And to do that, I want to quickly go over how we do weak gravitational lensing studies. What we do is we measure the ellipticities of galaxies. This is a Subaru image, and I've just shown all the ellipticities of the galaxies I've measured. Then we spatially average the galaxy ellipticities across the image to get the reduced shear, as shown here. These are whiskers, as we call them, and they're the magnitude and direction of the average ellipticity of galaxies. And they tend to be tangential to massive structures, as you can see here in the core of this cluster. And then through a convolution, we can recover the projected mass density map. And this is one of the most massive clusters in the universe. It's a few times 10 to the 15 solar mass cluster. And the resolution that we can achieve in this mass map is very dependent on the number density of galaxies that we're able to measure. And for ground-based observing, like with Subaru, we get about 30 galaxies per arc minute squared. Here's that same mass map with the Subaru data. And what I'm going to show you here is if we use Hubble, this blue outline of the ACS footprint, we can get about 60 galaxies per arc minute squared. So we've doubled the number of galaxies usable for weak lensing. And with that, we're able to discern substructures in the core of the cluster. This region here that were missed with Subaru because of the resolution we could achieve. So I think you know where I'm going with this. So Roman will be more efficient because it basically has Subaru's field of view. It has a very wide field of view, so we'll efficiently cover clusters, and it'll be far more effective. So it has a great resolution, which is valuable for separation of galaxies, more galaxies for weak lensing. And the redder filter set's a big advantage too, because it's better for fitting a smooth model to the red light distribution, and we get a better detection of high redshift galaxies. So it moves our background galaxies to higher redshift, which gives us more. And at about 27th magnitude, I predict there's about 150 galaxies per arc minute squared that we can use for weak lensing. And now I'll demonstrate what that 150 means for weak lensing here with a simulation. So this is a TNG cluster simulation. This is the projected mass density map. It's 10 megaparsecs by 10 megaparsecs cut out from this cosmological simulation. In the center, we have a 10 to the 15 solar mass cluster with 2 peaks here in mass density, and a few 10 to the 14 solar mass companions. And this is about 40 arc minutes across, so about the field of view of Roman. Starting with ground-based 30 galaxies per arc minute squared, we can detect the cluster in the core. So here I've zoomed in just to the cluster in the core. We get a detection, but it's not very well resolved by weak lensing. And we can detect those low mass substructures at low significance, those 10 to the 14 solar mass clusters. With Hubble-like imaging, I've kind of cheated and said it's 5 arc minutes, which is a bit bigger than Hubble, right? But close enough. At 60 galaxies per arc minute squared, we can really start to resolve the substructures in the core of the cluster, but we get absolutely nothing out here unless we want to expend a lot of time trying to do some kind of mosaic imaging. This is what it looks like with Roman. So with a large field of view and a very high number density of galaxies, we get a very nice resolution in the core of the cluster, able to pinpoint where the dark matter peaks are, even on the lower mass substructures, and we can get the detections of those companions. And I think that Roman will unlock the next frontier for weak lensing, which is the detection of the large-scale dark matter filaments that surround these clusters. So as you can see, I've changed the background scale to log so that it's easier to see where the mass distributions are. And the white lensing contours trace the filamentary structure that spans between these companions of this cluster. So Roman will be able to detect and characterize the dark matter content of the large-scale filaments. So in summary, the field of view resolution and filters of Roman are of great advantage for weak lensing studies and the large-scale structure. And I think the biggest improvements will be on pinpoint accuracy for the location of dark matter centroids, which is very important for constraining things like the self-interaction cross-section of dark matter. Detection and identification of substructures, so we can understand how these clusters have built up, robustly characterizing the dark matter of clusters, and start to map the large-scale dark matter filaments of the universe. Thank you.
Kyle, let's take a question or two. We got Lee there.
Kyle, what does this have to do with microlensing? That was the joke question. Kyle works on microlensing.
So the joke is that I'm in the MSOS team and I'm doing microlensing.
It's lensing.
It's lensing. It's all the same. Yeah.
No, the real question is, so for studying the structure of the clusters, is it more efficient, I don't know if I've asked you this before, to do something like the high latitude wide area survey, given the density and the redshift of the clusters, or is it better to do a targeted cluster survey?
I think it really depends on what the physics you're looking to understand is. Something like the high latitude wide area survey is great for looking for a wide variety of clusters. Whereas if you're really looking for something like constraining the interaction cross-section of dark matter, you really want those high impact collisions, and those ones are hot. They're detected by X-ray, so we know where a lot of them are. So those are the ones you want to do the pointed study. Yeah.
Go back and maybe follow up some of the ones that hit the outskirts of the space.
Yeah.
So just real quick, perhaps a naive question, but that Abel cluster you showed with the HST imaging, I noticed a bright foreground star on the right, and there seemed to be a contour that kind of went out around that thing. And so I was wondering, are bright foreground sources like significant contaminants for this kind of measurement?
Was it this one? Oh. Or the other one?
I think the first one you showed. The first HST image that you showed. Right there.
No. So this map is very similar to the strong lensing map, and there's actually a substructure there hidden behind. You can kind of see the bright galaxies that are associated to it there. So
cool.
These ones here. Yeah.
Just a weird placement of the star, I guess.
Yeah, unfortunate, I would say.
Thanks.
Thanks. Let's thank Kyle one more time.